All right, well, welcome to our free GMAT prep hour for February 2020. I'm Dmitry. I'll be talking to you about exponents today. Today is going to be an exponent workout. So I want to make sure we all have the skills we need. If you already have those skills and feel pretty good, we'll speed it up. If folks need some review, we'll look there. But want to make sure that we're doing everything we can to get cozier with exponents on the test. So we're going to talk about just what are the moves that are available, then how we can deal with matching powers across sides of an equation or a fraction, and how we can put that all together on some harder problems to make it all work for you. We'll be using a polling function. So what I'm going to do right now is I'm going to send you an A through E poll. And what I'd like you to poll in is your comfort with exponents. C in the middle would be, I know the basic rules. E would be, I'm terribly confused by exponents. I'm terribly confused by typing. Terribly confused by exponents. And, A would be, I feel very confident tackling these problems on the actual test. GMAT questions, not just the basics. Okay, see in a range. No one's polling in like, hey, what's an exponent? But I've got a bit of a range here. A lot of you feel like in the middle. So let's do a quick review of our rules. Most of you are saying you know the basics. So I certainly don't want to use up our workshop on that, but I want to give you a few minutes to just make sure that we know those moves. So I'll also do an A through E poll there. So what I'll have you do is just pull in A when you're ready to discuss these. If you're ready almost immediately, then you can pull in an A almost immediately. I just want to see where people are. So let's test some of your basics. Again, just pull in an A as soon as you're ready to discuss. Okay, I'll stop you there. If you're still working, we're going to go over these answers just to make sure. So we feel pretty good about these. Any that bug you? Looks like most people were pretty quick to say, got it. So that's fine. If you're watching this on YouTube, you can pause this and take a little more time as needed, but I'm going to pop up the answers. Most of these are things that we want to know pretty routinely. The one thing we want to watch out for are the ones that can't really be simplified. So does anyone see which one could be seen as maybe a trick answer, that there's not really anything we can do? Yeah, we can't really square root x plus y. I mean, we can rewrite it, but all we can do is say it's the half power, which is just another way of saying the square root. It's very important that, and I see even when with my higher scoring students, some people want to write this as, hey, root x plus root y, pardon the slop with this, right? They'll write that. No, it's not the same thing. No, right? Can't do that. And you could test that really easily by square rooting some known quantities, right? Imagine I had something very simple, like what's the square root of 25? Well, we all know what that is. But if I did the square root of 16 plus 9, well, that's 25. But if I squared them individually, I'd be like, oh, that's root of 16 plus root of 9. Oh, that's 4 plus 3. Oh, 7. Great. So square root of 25 is 7. Ah, no, this can't be right. So the reason I bring this up, you may feel very good about that, but it's just a quick reminder sometimes that when we're in situations where we are in a hurry, we're trying to guess an answer, we're distracted by something else, we might make decisions that we otherwise would not make. And I see the same thing with exponents, not just root things like that. I'll see, for instance, what is 10 to 5th minus 10 squared? Oh, sorry for the technical trouble. Looks like I lost everyone for a second. So I was just saying, if I had 10 to the 5th minus 10 squared, well, what is 10 to the 5th? What am I dealing with there? Am I coming through? If I have 10 to the 5th minus 10 squared, I can count with tens that the exponent is just a number of zeros. So it's just 10 times 10 times 10 times 10 times 10, so like this. So if I were going to approximate this, just roughly, how much is that? How much would that be? Yeah, that would be about 990, right? So basically 100,000, right? Is the board coming through now? So we can basically just say it's roughly the first one. The funny thing is I've seen people in the middle of a problem just really quickly want to say, oh, that's 10 to the 3rd, right? That's not right. And they know it when they're on a, when they're in a better frame of mind. But in the middle of doing something, they'll be like, hey, that's 10 to the 3rd. But wait a minute, 10 to the 3rd is just 1,000. How could 100,000 minus 100 be 1,000, right? The 100 is barely a rounding error, right? If you won a $100,000 prize and you had to pay a $100 tax on it, you'd be like, great, that was less tax than I was expecting, right? It's barely an issue. Okay. So we're just watching things like that. Let me just throw the answers up to all these. Everyone seeing everything okay now? So basic rules, when we divide, we subtract our exponents. When we multiply, we add them. That actually creates these other two rules on the right. If I subtract equal amounts, I get 1. So at some point in school, I remember just being told, hey, 0 powers are 1. And I was like, okay, that's weird. So 5 to the 1 and 3 to the 1 and negative 2 to the 1 or to the 0 are all the same thing. They're all 1. That's weird. But it makes sense if we think of it as like, oh, if I have x to the 5th divided by x to the 5th, well, I'm committed, if I have this little game I'm playing of exponents, I'm committed to saying that that means x to the 0. Right? That equals x to the 0. But it also means something divided by itself, which of course is 1. So one way to think of a 0 power is that I'm not multiplying or dividing, or that I'm multiplying or dividing by the same amounts of this. It shows up in combinatorics if you're like trying to figure out how many ways to combine some prime factors or something like that. You might say, well, I can multiply in this many 2s or this many 3s, and how many 5s? Oh, I don't have any 5s, so I'm just not multiplying by anything. So that's where x to the 0 being 1 can be interesting, but it's something we can still memorize. And it then also follows that if I have more on the bottom than the top, I'm just going to put it on the bottom, right? I'm going to say, oh, I'll get a negative exponent if I have, say, x squared over x to the 8th. The rules of the game tell me that I subtract, and get 2 minus 8 is negative 6. But I can also say, well, if I have a bunch of x's on top and even more x's on bottom, I can also just see that most of them will cancel out on the, well, all of the top will cancel out. And I'll be left with 1 over x to the 6. What happens if I have something like 1 over x to the negative 6? What do I do with that? Yeah, it flips to the top. Yeah, x to the positive 6, exactly. I gotcha. So one way to think about that is it's almost like, I know I'm weird, but I think of it as, you ever in the water and you have like maybe a floaty toy for the pool, one of those noodles or a kickboard or something like that, and you try to push it out of the water and it just wants to pop back out. I think of negative exponents like that. They want to pop across. If I've got a negative on the bottom, it wants to go to the top and become positive. And if I've got a negative on the top, it wants to go to the bottom and wants to be positive. So negative ones like want to go to the other part of the fraction. They want to switch from top to bottom or vice versa. And if we can do that and flip the signs, then it's just easier to think about. So if I had something like, y to the negative third over, let's say if it's even y, let's say a y to the negative third over y to the negative fifth, someone who feels pretty comfortable with this might just say, oh yeah, well, negative 3 minus negative 5 is positive 2. But they might be more comfortable saying, can I just flip that? That's y to the fifth over y to the third, and then I can think about it, right? So there's nothing wrong with doing it right away, of course, whoops. But it might make my life easier if I just say, oh yeah, look, that's gonna be y squared. Let me get it in terms that make more sense. Sometimes we see that combined with fractions. Fractions to negative values just turn into integers a lot of times, or at least. Okay. We know we can split up terms. If I have, 20 squared, I can have 2 squared and 10 squared, or break it up into other ways, right? 4s and 5s. If I raise a power to a power, I'm just saying x squared times x squared times x squared, I multiply it out. And then this is a different story. I want to just be careful not to distribute over addition with an exponent. I want to multiply and FOIL it out. This is your common quadratic pattern that you want to see. So be very careful. You don't just square this and square that. You can do that with multiplication. You can't do that with addition. In that sense, it's kind of the opposite of the distributive property. If I have 5 times AB, it's not 5 times A times 5 times B, it's just 5 times AB. Whereas if I have 5 times A plus B, it is both, right? And this is kind of the opposite of that. Here, when I multiply, I have to do all the individual pieces with addition. Whereas if I apply an exponent to multiplication, I just tack it right on. Okay. Questions on that? We okay? Let me start kicking it up a few notches here. All right, so I want to now look at some additional moves you can do to make sure you're comfortable with. Some you may already know, some you may not, but let's just apply to these. Again, I'll let you pull in when you're ready to discuss, and so if that's very quickly, that's fine, but just pull in whenever you're ready to talk about this set. All right, let's see what we can do with these. I know some of you may still be working, but want to get a feel for these. These are all going to be solvable using some combination of the rules that we know, though in some cases it might help to infer one more rule if we don't already know it. And so this first one is a good example of that. So one way I could certainly break this down is to recognize, hey, 3 and 12 go into 36. Maybe I want to break 36 down. At the extreme, I could break this all the way down to prime factors. I try to avoid doing that if I don't have to. Right? Imagine, I don't know, I made some really good chocolate chip cookies and you asked me for the recipe and I broke it down to like the actual elements. You know, here's how much nitrogen and hydrogen, and you might say, whoa, that's it's farther broken down than I wanted. Just what are the basic ingredients, like, you know, chocolate chips, flour, cinnamon, like what's in there, right? I don't need to know how much nitrogen is in it, right? I don't necessarily need to break down to prime factors. It'll work. If I break 36 and 12, and of course 3 already is prime. If I break those down to the prime factors, I can do it. It's just overkill a lot of the time. So one way I could do this is to recognize that 36 is 3 times 12. And we can use the rule we did on the previous page where we distributed to both. And if I have that, and I have here, I know I have 3 to the 4th and 12 to the 5th. I can just distribute that 5 and say, okay, well then I'm going to have 3 to the 5th, 12 to the 5th, over 3 to the 4th, 12 to the 5th. And this is not too bad. And I can get to an answer that way. The 12 to the 5ths cancel. 3 to the 5th over 3 to the 4th is just 3, right? 3 to the 1. My answer is 3. However, if I know that I can break this 36 down to 3 and 12, I might also notice, well, if that's going to cancel and I have these 5s here, I don't actually need to factor it. I can divide directly. So one rule that people, for whatever reason, tend not to realize exists is that if the exponents are the same, we can multiply or divide the bases directly. We still have to keep the exponent, but no matter how many times 36 divided by 12 is 3, it's going to keep being 3. So in other words, I could just directly say, hey, if I've got 36 to the 5th here, and I got 12 to the 5th there, and of course I have 3 to the 4th also, just line those up, it's just going to be 36 divided over 12, 36 over 12, 36 over 12 over and over again. Each of those is 3. So I can just turn this directly into the 3 to the 5th over 3 to the 4th here that I got to eventually when I cancel the 12s. I don't need to take the intervening step of breaking this down. And this can be very useful, especially if I don't know how to break things down, right? If I have, say, you know, x to the y over z to the y, I don't have to know what any of those are to say, oh, that's the same as x over z to the y, right? I don't care what those mean, that's just true, and I can do that. And the same thing when I'm multiplying, right? If I have 5 to the 9th and 26 to the 9th, I can just multiply those together and get 130 to the 9th. By the way, I hope you all know your 5 trick. It's for mental math, it's one of the quickest, easiest things you can learn to help you on this test. If you want to multiply by 5, multiply by 10, chop it in half. So if 26 times 10 is 260, 26 times 5 is half that, is 130. Okay, but I can just directly multiply, okay? Next one is just like we were doing before, 2 to the 6 times 2 to the x is just 2 to the 6 plus x, whatever that is. Now, the next one with 3 to the 8th, notice that I had this show up a couple times, 3 to the 8th in different forms. So what I do with this, I actually have some options. What's one way I could combine 3 to the 8th times 3 to the 8th? What's a potential answer? And so in saying, do you keep the exponent the same and don't add them? That's right, right? You keep the exponent the same. Because what I'm saying is, I mean, one way to think about this is regrouping it. If I have 5 times 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 5, and 26 times 26 times 26 times 26, all those times, I can really say I have 5 and 26 and 5 and 26, and 5 and 26 9 times, right? Imagine if I have 2 to the third, 5 to the third, right? Okay, well, that's 2 times 2 times 2 times 5 times 5 times 5. But I could also say, hey, that's 2 times 5 times 2 times 5 times 2 times 5. So that's just 10 to the third. And of course, it has to be true in reverse. If I said, what's 10 to the third divided by 2 to the third? Well, it has to be 5 to the third because we just did it. And multiplication and division reverse each other, right? But I could write it as 10, 10, 10 over 2 times 2 times 2. And each of those 10s cancels out of 2 and gives us a 5. Like that, right? And that's what we'll have left, 5 to the third. Okay. So then I got some feedback on the last one, 2 different answers, right? If I use the same exponent rule, I would not add the exponents. I would just multiply the bases. 3 to the 8th times 3 to the 8th is 9 to the 8th. It's 3 times 3 times 3 times 3 a bunch of times, and then a bunch of more 3s a bunch of times. It's a bunch of 9s, right? Whereas if I use the same base rule, then I would keep the base and add the exponents. 3 to the 8 plus 8 is 3 to the 16. And you can prove that these are the same thing, right? Because if I were to rewrite 9 as 3 squared, right, it'll lead to the other, right? 9 is 3 squared. And whoops, not 3 to the third, that's wrong. 3 squared. And when I raise that to the 8th, I get 3 to the 16th. So they match up. But the point is, that's just proving it. We wouldn't want to do that. If we wanted that, we would have done it the other way. The point is I have 2 different ways I can write it, which is why I gave you 2 different problems involving this afterwards. What you do, and this is true for so much of the GMAT, what you do, which move you make is probably going to depend on what you're trying to go to, where you're trying to get to with this. So if my bottom has 9, I'm probably better served by getting this in terms of 9. Hey, this is 9 to the 8th, and this is 9 to the 5th, and now I can just use my usual subtraction rule. Hey, that's 9 to the 3rd, or if I wanted 3 to the 6th, if that were the answer choices, what they had. Whereas if the bottom is in terms of 3, then why not keep the top in terms of 3? Use my 3 to the 16th and my 3 to the 12th. And again, I'm looking at what I want to do. Sometimes I see people do exponent problems, and it's like they're making art. They're like, well, I can do this move and this move and this move, but they end up going in circles. And so I want to look at where I'm trying to go. What kind of result am I trying to get to in terms of the answer choices, or what am I trying to eliminate? So if I see on the bottom I've got a power of 3, I'd like to get a power of 3 on the top so I can cancel it. Okay, questions on that? All right. Then what about this bottom one? If I have 7 to the 10th over 14 to the 10th, using what we've now learned, what can I do with this? If we picture it, we've got a bunch of 7s on the top. And I've got a bunch of 14s on the bottom. Yeah, I can break it down, but I actually don't have to. I don't have to break the 14 down to 2 times 7, because I can simply say, I know what 7 over 14 is. So one way to view that is to say, hey, I'm going to get a bunch of 2s on the bottom and a bunch of 1s on the top. Every time I cancel a 7 with a 14, I get to get a 1 on the top and I get a 2 on the bottom, right? So one way to see this is that I'm going to get 1 to the 10th on the top, which is very interesting, right? But it's 1. And I'm going to get 2 to the 10th on the bottom. When you have a fraction with 1 on the top, it doesn't matter whether you call it 1/2 to the 10th or 1 over 2 to the 10th, right? The 10th on the top doesn't really make a difference. If it were anything else on the top, it was like 2/3, and of course it matters that there's a 2 on the top. It'd be 2 to the 10th over 3 to the 10th. But I could also think about it as, hey, again, if I'm dividing directly, I could just say, hey, 7 to the 10th over 14 to the 10th is the same as 7/14 to the 10th, which equals 1/2 to the 10th. We can call this 1/2 to the 10th. We could call it 1 over 2 to the 10th, or if you like, we could call it 2 to the -10. Those would all be the same thing. Okay, how we feel about that? That feel okay? I want to make sure we remember this rule. This is a rule some of you have seen. Some people tell me they haven't seen it or don't remember it, but I feel like it's the one that tends to get overlooked the most, and it's a really powerful rule when you know when to use it. Anytime the exponents are the same, we can multiply or divide the bases directly. We have to keep them the same though, right? Sometimes I see people doing this mistaken move. They'll have something like 3 times 2 to the 40th. And they'll try to tell me, I want to make sure I'm showing bad math here. This is bad, right? But they'll try to tell me that this is 6 to the 40th. Well, just like the 10 to the 5th minus 10 squared doesn't subtract, right? I can't, or it doesn't subtract directly from the exponents. I can't do this because I've got 42s and only 1 3. So this is 2 to the 40th times 3. There's not a better way to say that unless you figure out what it is, right? It is not 6 to the 40th because it's 3 to the 1, 2 to the 40th. To get 6 to the 40th, I'd have to have had 3 to the 40th. If I have 40 powers of 3 and 40 powers of 2, then I have powers of 6, yeah? But here I just have 40 powers of 2 and 1 power of 3. Okay, so if we can do that, then it's a matter of applying this to other ways that they might use this, right? And one thing we'll see is that they'll give us strings. Just like I was trying to add, or subtract 10 to the 5th minus 10 squared, they might give you situations where you have to do that. And the question is, what can we do to make that happen? So let me actually just, rather than time you on this one, I'm just gonna look at these. Let's say I'm trying to do something like this: 5 to the 4th plus 5 to the 5th plus 5 to the 6th plus 5 to the 7th. There's no simple rule that allows me to do that. It's not just like, oh yes, it's 5 to the 12th or something like that. But yet the numbers are big enough that I don't want to just find out what they are. I mean, with powers of 10, even when they're big, at least I can write them very easily. But 5 to the 4th is 5 times 5 is 25, times 5 is 125, times 5 is 625, and then 5 to the 5th is 5 times that, and 5 to the 6th, that's more than I'm going to do on a GMAT problem, right? That's more than I'm expected to do arithmetic-wise. So what can I do to answer this question? Anyone know a move I can do? Yeah, I can take one out. When I take it out, the idea is I can factor out, right? So factor out a common term, right? So there's one thing I should say is there's no rule for these. And what I mean by that, you can say there's rules for everything, but there's no rule of like when you add powers of something, this is what you do to them. In fact, most of the time you won't get a power. For instance, let's look at, say, just the first 2 terms, 5 to the 4th plus 5 to the 5th. Well, what will that be? Well, 5 to the 4th, like we said, is 5, 25, 125, 625. And 5 to the 5th is 3125. If we put those together, that's like 37, 38-ish. That's not anywhere near the next power, which is like 15,000. So what we know is we'll get a number that's bigger than 5 to the 5th, but only by a little bit. Just like when we subtracted 10 squared from 10 to the 5th, we got one that's smaller than 10 to the 5th, but only by a little bit. It wasn't small enough to be down to 10 to the 4th. So anytime, and this is a general rule, anytime you add a lower power to a higher one, you're not really going to go up to the next higher power. And anytime you subtract a lower power from the higher one, it's not going to be enough to drop you down to the next lowest power. That's what the idea of being exponentially bigger means. And so it's not going to even be a power of 5. The only exception is if you have enough to make the whole a power of 5. In other words, if I have 5 different powers of 5, then they're another multiple of 5, and I can get an extra power, but that's the exception. So here I could say, if I pull out a 5 to the 4th, I could see how many times 5 to the 4th goes into each of those. 5 to the 4th goes into itself once, don't skip that part. How many times will it go into 5 to the 5th? What's 5 to the 5th divided by 5 to the 4th? Anytime we have the same base, we can just subtract the exponents. 5, right? So we could just say, hey, this is 1 plus 5 to the 1, and then 5 to the 6th divided by 5 to the 4th will be 5 to the 2, and then 5 to the 7th divided by 5 to the 4th will be 5 to the 3. And you can prove that just by subtracting 4 from each of those, right? We get 5 to the 0, 5 to the 1, 5 to the 2, 5 to the 3 in a nice order. Now, why is this helpful? Well, it makes the numbers more manageable. Sometimes they might actually have you calculate this, but they might just have you add this up. Let's see, that's 1 plus 5 plus 25 plus 125. Hey, these are small enough numbers now that I can kind of handle them. That's what is that? 125 plus 25 is 150, 156. So that's 5 to the 4th times 156. I wouldn't be at all surprised if the GMAT gave you an answer in that format. If we had to, we could figure out what that is. It's ugly, but we'd at least have an idea. And then if I had to approximate by, say, the units digit, it ends in a 0. You know, it's more than 100 times 625, so it's more than 62,000. I could do that kind of thing. But that's beyond the level of arithmetic the GMAT's usually asking you to do. You probably notice it's not a lot of like grinding out a bunch of multiplication with a bunch of places. So we could do the same thing if the powers are unknown. I can pull out whatever x is. I can pull out a 2 to the x and say, all right, well, 2 to the x goes into itself once. How many times will it go into 2 to the x plus 1? How do I get from 2 to the x to 2 to the x plus 1? If I do the division again, 2 to the x plus 1 over 2 to the x, I'll get 2 to the x plus 1 minus x is 2 to the 1. But if this is not natural to you, I want to push you on this, because this is something that you want to have just automatic. That when you increase the base, when you increase the exponent by 1, you're just multiplying by the base. And if you just decrease the exponent by 1, you're divided by the base. So every time we increase or decrease the exponent by 1, we're simply multiplying or dividing by the base, right? When I go from 10 squared, which is 100, to 10 cubed, which is 1,000, I'm just multiplying by 10. And when I go from 81, which is like 3 to the 4th, and I go down to 3 to the 3rd, I'm just dividing by 3 to get 27, just going in that way. So I can say, hey, this will be 1 plus 2 to the 1, whatever that is, right? Whatever that is, it's 2, plus 2 to the 2. And again, this becomes something solvable now. I can say, oh, 2 to the 2 is 4, 5, 6, 7. This is 2 to the x times 7. Now, why would they give you something like this on the GMAT? We'll see in a little bit that they can tie this in with divisibility. They might say something like, which of the following prime factors does this sequence have? It is in no way obvious from glancing at it that 2 to the x plus 2 to the x plus 1 plus 2 to the x plus 2 has to be a multiple of 7 no matter what x is. That's not obvious at all, but it's actually true. Unless, of course, x is some funky negative number where it becomes a fraction. But other than that, then it has to be a multiple of 7. As long as x is, 0 or greater, then whatever this is a multiple of 7. If x is 0, we have 1 plus 2 plus 4, right, which is 7. If x is 1, we have 2 plus 4 plus 8, right? But whatever you have, you're gonna get that same kind of thing. Okay. Sometimes you'll see cases where you actually don't want to do this trick. Can you see why we don't want to do this trick on the next one? What's our common term here? 2 to the 5th, 2 to the 4th, 2 to the 3rd, 2 squared, 2. My only common term is 2. So I can pull a 2 out, but what a waste of time. Now I'm just going to have 2 times 2 to the 4, 2 to the third. I'd rather just find out what this is. And hey, use your fingers. 2, 4, 8, 16, 32, right? I'd rather just do that. 32 minus 16 minus 8 minus 4 minus 2. You'll notice that it keeps chopping in half. 32 minus 16 is 16. 16 minus 8 is 8. 8 minus 4 is 2. Is 4. 4 minus 2 is 2. Right? So I could do all the work to figure that out, but I'd rather not. Right? Okay. Whereas if I have big numbers, I have to do a trick. Right? So here I'll do 5 to the 37. It's our common term. And I'll take that away. So I'll have 5 to the third plus 5 squared plus 5 to the 1 plus 1. Same deal. Sometimes I have to do a little bit of uglier math, but nothing too terrible. It's 5 to 37 times, again, 125 plus 25 is the same thing as we actually had above, right? 5 to the third squared first 1, right? So it's actually very similar to what we had on the top one, just an uglier thing on the outside, but the underlying thing is the same. All right, Jay, you got it. Yeah. It looks like it might zero out, but then we got a little bit of edge. And if you pull the 2 out, you'll see the same thing. And one thing you'll know is it'll never be, because if you take away all the subsequent powers of 2, or all the lower powers of 2, they together still won't add up to 2 to the 5th, because 2 to the 5th is double of 2 to the 4th, right? Oh, no. Thank you, Lily. You caught my. I messed up my own problem. Yeah, it has the same powers. No, I'm sorry. We're supposed to be subtracting. Yes. This is a really good example of how we can be right and wrong at the same time, where we can have all the right stuff and we can understand, and we can still end up doing it wrong. It's so easy to get in trouble with that. So I'm sorry. No, we want to do 125 minus 25 minus 5 minus 1. Thank you. So that's going to be what? 125 minus 25 is 100, minus 5 is 95, minus 1 is 94. Thank you. 5 to the 37 minus 94. That's what I get trying to lean too much on the other stuff. All right, good. Thank you. Good. All right, so these are our moves. If you want to try this out on an official problem, I'm not allowed to share this problem, but if you have an official guide, pretty much any edition of the official guide, try PS number 30. Sorry, 230 for a variation on this. One of the tricks is that it's set up as a little bit of a word problem, but the other trick is that it deals with negative powers. And so you might have to think about it. If I have negative powers, what's my lowest common, or what's my greatest common factor? What's the lowest term, right? If I'm adding, 3 to the negative 40th plus 3 to the negative 39, which of those do I want to pull out, right? Which of those is actually bigger and which of those is actually smaller? So we have to think about that when we do number 230. So if you want to try that, if you have an official guide, any of the recent editions, it'll be number 230. Cool. Oh, some of you already done it. Great. Let's keep it moving. I'll try some full GMAT style problems now. So let's take a moment to try this set, and I'll just talk to you in a minute on these. All right, let's go ahead and have you pull in your answer for the first one here, the one up top here with the 36. Pull that in when you got it. So with these, sometimes it can be helpful to estimate and just get a sense of how big or how likely an answer is to be a certain size. Notice we have quite a range from 0 to small fractions to larger integers, and we want to have a sense of what's reasonable. If you think about my swimming pool toy analogy, you can say, hey, I want to put this one down and I want to put these ones up, and that's probably going to make my life a lot easier when I try to think about this. So if I just take a moment to swap this and say, hey, this should be 3 to the fourth, 2 to the fourth, and on the bottom, 36 to the third. Now I can already start thinking about, does that mean that the top or the bottom is bigger? What do you think? Does it look like the top or the bottom is bigger? These have slightly higher exponents, right? But the pieces are smaller, right? It sure looks to me like the bottom ought to be bigger, which makes it seem like D and E are bad answers, right? So if I get one of those, I want to catch that and go, wait a minute, that probably wasn't right. And I do this all the time. I make lots of mistakes, but I catch not all of them, but I catch the great majority of them from saying, what is it that I'm looking for? Does this even make sense? So then I could break this down if I want. I could call this, for instance, 6 to the fourth. Would you want me to do it? And I know that 36 is 6 squared. Now I can put those together and say, oh, that's 6 to the fourth over 6 to the sixth. That is not 6 to the 4/6, but it is 6 to the negative 2. And that's not a negative number, it's 1 over 36. All right. That's our move there, but we want to at least be able to predict it a little bit. Similarly, on the next one, we should be able to predict a little bit what kind of answer we want. Because notice what we have on the top. If I have 9 squared to minus 9 to the fourth, I might not know offhand what that is. It's kind of a funky answer. But what do I know about it? What do I know about 9 squared minus 9 to the fourth? I'll let you pull this in when you're ready. What do I know about 9 squared minus 9 to the fourth? I know it's got to be negative, right? Must be negative. If I take a bigger number from a smaller number, it's got to be negative. So if I just look at the top and say, hey, negative over positive, then I know my answer is negative. And the beautiful thing is, then I don't need to do any of the work at all. I like exponents. I like playing with them. That's the point of today. But look, these are all out. If I take a bigger number from a smaller number and divide it by a positive number, 9 squared, of course, is positive, then I don't care what it is. I can do it. I could say, hey, it's 81 minus 81 times 81. I don't want to figure out what that is. I don't have a calculator. Over 81, I could do this. Do one way to do it. I could also do what we did earlier and pull out a 9 squared, right? But in a sense, that's what we can do here, because we can just say, oh, if I divide both of these terms by 81, that's a 1 minus 81, negative 80. But I could also pull out a 9 squared and say that's 1 minus 9 squared. And then I've got all over 9 squared. Those cancel, and again, I have 1 minus 81 is negative 80. Cool. All right, pull in the last of the set. Well, fair amount of agreement on this. A lot of people might guess that the 7 has to be in the answer because 7 doesn't go into 6, right? But there's a trick, right? There's a trick. One way we can see this quickly is to divide 6 squared out of both terms. I could say, hey, 6 cubed minus divided by 6 squared is 6. And 6 to the 4th divided by 6 squared is 6 to the 2. So I could say 36 plus 6 over 7. Okay, that's 42 over 7, and that's just 6. That'd be one way to see it. Another way to see it would be to pull out a common term, right, like we were doing earlier. If I did that, it actually comes to kind of the same thing, but not entirely. So I'd say, okay, this is 6 plus 1. In some ways, this is actually nicer because I can see right away when we're thinking in terms of divisibility that, hey, the 7 is going to cancel. 6 plus 1 and 7 are the same thing. And so I've got 6 cubed over 6. But I could right away see if I were trying to deal with divisibility or something like that, I could see, oh, there's no 7 in this. It goes away. All right, nice. Excellent. So let's move beyond those mechanics and look at some ways that the GMAT expects us to manipulate these things. So one thing you'll see a lot of is the idea of matching up prime factors. So a couple problems on this theme. The first one is from MBA.com. It's in the free set there. And the second one is one of ours. But they both work on the theme of, hey, when I have some powers over here and some power that I can express on the other side, how do I match those up? So see if you can play with these. When you're done with both, pull in your answer for the first one. So finish both first, and then pull in your answer for the first one when you have it. So I'll give you a moment to do that. Here we go. Okay, even if you're not done with the second one, go ahead and pull in your answer for the first one. Just see how we're doing on this. So good, I'm seeing some good answers here. One thing we want to be able to do is just recognize how to combine the left-hand side, but we want to make it fit with the right-hand side. So we know that if we have 2 to the x and 2 to the y, right, we can just put those together, right? It's like x powers of 2 and y powers of 2. So we'll have x plus y powers of 2. But 8 by itself isn't very helpful. We want to express 8 as a power of 2 as well. So 2, 4, 8, it's 2 to the third. Now, one thing we could do, if you want to get geeky about it, you could say we're exponentiating this equation or taking the log of both sides. If you don't want to get geeky about it, what you can say is, hey, if 2 to the x plus y is the same thing as 2 to the third, then x plus y has to be 3. Right? You just logic it out. X plus y has to be 3. So we could get an equation, and what you'll sometimes see is that exponent problems will turn into algebra problems. In other words, they'll turn into non-exponent algebra problems just by us saying, oh, 2 to the x plus y has to be 2 to the 3, so x plus y must be 3. Oh, and now I just have an equation for x and y. Now I could take the other equation, 9 to the x, or you might call it 3 squared to the x, times 3 to the y equals 3, 9, 27, 81, 3 to the fourth. Right? So I can say, oh, 2x plus y equals 4. Generally speaking, if I'm trying to combine equations on the GMAT, my safest bet is to stack and eliminate something. So here, I'll say, okay, 2x plus y is 4. And I want to add a negative or subtract, however you want to think about that. So if you haven't done this elimination technique, it's very powerful. I would call it my plan A on most problems that involve simultaneous equations like this. And I'll just get x equals 1. And then I can plug that back into either equation and get my other one. So if x is 1, y equals 2. And our answer is okay. So we can do a similar thing on the second one. If we know that 4 to the m. So someone's asking, I wrote the second equation as 9. 3 squared gives me 1 and 1, 2. Well, no, actually, without the first equation, you don't know the relationship of x and y. So you know that 2x plus y is 4, but you wouldn't know whether that's the only way to get there, right? So for instance, in theory, x could be 2 and y could be 0 or something like that. So if they haven't given us any constraints about integers, non-zero, non-negative, heaven forbid one of them's a negative, so we do need the other equation to be sure. Yeah, they're equal to 81, but we don't know that both x and y are positive integers. If they are, then it's a lot more constrained. You'd say, all right, well, it's not going to be like x is 4 or something like that, and then you can do it. Yeah. So we can do the same kind of thing here. Usually when they give us a second equation that's not a distractor, I'll show you how they can distract us a little bit, including right here. Notice that on the left we have some 2's and some 3's, and but they're only asking about the one with the 2's. And so we can basically ignore the 3's. And how do we do that? We just say how many 2's are on the right. I don't care about the 3's. I can break this all down. I can say 2 to the 2m times 3 to the n is equal to 2 to the 6, 3 to the 6. But notice that I don't need both parts if what I'm concerned about is m's and n's. And one thing that's important to recognize with primes is that they don't mix and match. In other words, if some number of 2's and some number of 3's gives me 6 2's and 6 3's, it's going to be that the 2's were 6 and the 3's were 6. In other words, it's not going to be, oh, well, it could also have been that there were like 8 3's and 4 2's. No, it wouldn't balance out. Primed, it's like when I was talking about nitrogen and hydrogen, like the periodic table. It's got to be that. If this breaks down to 3 6's, 6 3's and 6 2's, then that's what we have on the right. So I can just match one of them. I don't have to match both. I can just use this alone. Might feel cheap, but I can do it and say 2m is 6, m is 3 without a need for looking at n, although obviously n gives me the same result. Well, m gives me that, sorry, the n is 6 gives me a different result. It tells me what n is, but I don't need that part. I just want to know it now. Sorry. Okay. That all feel all right? So that's the kind of thing where we're trying to put pieces together and match sides. And sometimes they'll mess with us a little bit like that. Let's look at a couple other variations real quick here. Oh yeah, we're running short on time. So let's just do one more. This is a fun one because I can build a variation on it. So try this out and pull it in when you have it. I can add an extension for anyone who gets done early. It's something to think about. If you get done early, see if you can do my extended version without cheating too much off the one we just did. Okay, so looking at the original one on the top, how do I start? If I know my 4 and 5 on the left have to match my 4 and 5 on the right, yeah, I can move this around a little bit, right? So I could say, how many 5s are in 400? I could divide 400 by 5 and get 80. Divide 80 by 5 and get 16, right? I could also think of it as 20 squared. That might be a useful way to do it real quick. If I recognize that 400 is 20 squared, then I could say, all right, that's going to be 2 squared times 5 squared. So 4x, 5 to the y, 4 to the x, 5 to the y will be equal to 2 to the 4th times 5 squared. Various ways you could have broken that down. You can also say 4 times 100, 100 is 10 squared, whatever works for you. And then I just want to think about what that means. So I could say, all right, well, maybe I didn't even want that 2. Maybe I wanted a 4. I could have just said, 4 times 5 squared. Maybe it would have been better, right? So if I think of it that way, I could say 4 to the x, 5 to the y. Clearly, y is 2, right? That has to match up. And if I rewrite that as probably better as 4 squared, and x is 2 as well, right? So it looks like x is 2 and y is 2. Am I right about that? Whoops, no. So then I could say, all right, well, what do I want? What do I have at this point? I want to say this is going to be 4 to the 2 plus 1 and 5 to the 2 minus 1. 4 cubed times 5. 4 times 4 is 16, times 4 is 64. 64 times 5, you can use my little trick from before. 64 times 10 is 640. So 64 times 5 is half that, is 320. And that's our answer. And we can do it that way, and it works great. It works. But yeah, if we think about the extension, we might think of an easier way to do this, right? And I think we can make it even easier than you're saying, Lloyd. Let's think of it this way. When I take a number and I add 1 to the exponent, let's go back to what we talked about at the beginning. What am I doing to the number? When I go from 4 to the x to 4 to the x plus 1, what am I doing? Yeah, right? Adding 1 to the power of 4, adding 1 to the exponent of 4 multiplies by 4. And so what happens when I take 1 away from the exponent of 5? Subtracting 1 from the exponent of 5 divides by 5. Right? When I go from 5 squared, which is 25, to 5 to the first, which is just 5, I'm dividing by 5. So the net effect, I'm multiplying by 4 and dividing by 5. So it would just be 4/5 q. Or if you like, 4q over 5, right? 4/5 q. So if we recognize that reasoning, then we could do this other problem much faster. I don't actually care what x and y are. It doesn't matter. It doesn't matter at all, and that's what I want to stress here. So if we did all this work, we should be proud of our abilities, but we want to not do it. Because if I can just say, oh, 4/5 q, oh, my answer is just going to be 4/5 of 400. Right? A fifth of 400 is 80. 4 times 80 is 320, and I'm done. I do not need to find the values. And so one thing you'll see sometimes that'll get you on these when it comes to, say, data sufficiency, you'll think, ooh, if I know this, I can find X. And if I know that, I can find Y. And it might turn out you don't need to know that, right? They ask you, what's 4 to the A times 5 to the B, and then they tell you A is 1 more than X and B is 1 less than Y, and you say, oh, it doesn't matter what X and Y were, I'll get the same answer every time. All right. Fun stuff. All right. I hope people found that helpful. Any things you desperately want to remember? Not desperately, but you definitely want to remember from today? Any takeaways that you want to jot down? Oh, okay. We can talk about the nine to the power of 1 just a second. We'll look at that. All right. Glad that's helped. So yeah. So absolutely to add or subtract exponents, pull out a common factor. Really useful to be able to do that. Adding or subtracting from the exponent. Just multiply or divide the base that many times, right? And then hopefully we're remembering to use estimation and common sense to narrow down answers. Sometimes that can make your life a lot easier. Or to save work, as we just know what the answer is. All right, that makes sense? And yes, oh yes, matching primes is very important, right? Matching up primes to powers can tell us the powers even when we have unknowns elsewhere in the equation, right? So if I don't know the powers of the threes, but the twos match up, then that's the twos I have, right? So if I know 2 to the x, 3 to the z is equal to 2 to the 5, 3 to the y, right? Something like that. Then I know that x is 5, even though all I know about threes is z equals y. But what is that? But I still know x is 5. Okay. Cool. Hope that was all helpful. If you want to check out any of our classes, let us know. I'm going to stop the recording here, then we can take one more look at that other power.